This video is going to cover normalizing flows. The goal is to ultimately get an understanding of flow matching models, but we are going to get there in multiple videos, of which normalizing flows is the first one. Once we have understood this, we'll be able to convert simple distributions to complex ones, and even train a normalizing flow model for generating MNIST images. This aspect of learning to transform a simple distribution into a complex one isn't new to us. Variational autoencoder does the same. Using an encoder, we learn the parameters of the approximate posterior distribution so that we can reconstruct the images and even constrain that this is as close to a standard normal distribution as possible. Post-training, using the learned decoder, we can transform samples from standard normal distribution to a complex distribution, such as that of images in our dataset. Generative adversarial networks also allows us to do the same. Using a min-max game between the generator and discriminator, we end up with a generator that can again achieve similar objective: transform samples from standard normal distribution to that of data distribution. So if there are multiple approaches to convert simple to complex distribution, why bother about normalizing flows? Well, in normalizing flows, we explicitly learn the data distribution, and it allows us to compute the log likelihood in a tractable manner. Remember, in VAE, the marginal likelihood is intractable. So rather than maximizing log likelihood, we maximize the evidence lower bound. And in GANs, training does not have anything to do with likelihood. With normalizing flows, we can evaluate the log likelihood of a point, whether it's something that is very likely to be coming from the data distribution or very unlikely to be coming from that. Furthermore, we can also compute precisely which latent point, or rather point from the initial simple distribution, would generate this sample from data distribution. This is because every data point corresponds to a unique latent point. So how does this normalizing flow model actually work? Well, in order to get to that, we need to understand few relevant concepts first. If we know the distribution of x and want to know the distribution of y equals f of x, we can get that using something called change of variables theorem, which gives us the exact formula for computing it. In the scenario of generative modeling, if we think of a function f that transforms simple distribution into data distribution, then having such a mechanism would be beneficial in computing likelihood of transformed latent samples under the data distribution. So in this section, we'll try to understand this theorem, and in the next one, use it to train a generative model. This section, and in fact the entire video, assumes that you are aware of the distinction between probability and probability density. If not, then I would suggest to read up on that first, as there are tons of resources available explaining in a much better way than I can. But for completeness sake, let's go over this quickly. Say you have a continuous distribution and you are sampling numbers from it. What is the probability of getting exactly this number? It's essentially 0, right? Because there are infinitely many possible values between 0 and 1, and the chance of hitting this one exact point is really small. So it doesn't make sense to talk about probability at a single point when we are dealing with continuous random variables. However, we can say meaningful things about neighborhoods. For example, the probability of x being somewhere near 0.5 is much higher than the probability of it being somewhere near 0. That is where probability densities come in. It tells us how much probability mass is concentrated around a point. In one dimension, it represents probability per unit length. For 2D continuous random variables, it would be probability per unit area. And for 3-dimensional, it would be probability mass per unit volume, and so on. Points with higher density are where the random variable is more likely to fall, and points with lower density are less likely. Finally, to find the actual probability of x being in a region, we integrate the probability density of x over that region. With this very quick overview of probability and probability densities, let's get to change of variable theorem. Imagine we have a random variable x with probability density px. Let's say we define another random variable y as 2x. What can we say about the probability density py? Actually, let's be more specific. What would the density of y at a point be? It's natural to think that it should be density of x at y by 2, because after all x equals y by 2. But is that correct? The fact that we are talking about probability densities, we know for both px and py, density at any point cannot be less than 0, and total probability over the entire space must sum to 1. These two statements would be true for any probability density function. Like for example, this is what density of A, which says a uniform random variable from 0 to 2, would look like. The density at all points would be same, which is 0.5. And we can see that the total area ends up to be 1, matching the second requirement. So similar to the previous question, what if A is a random variable with value 1/4 of its previous value? So now it would be A from 0 to 0.5. Think of this wire representing the probability mass, the length representing the range of values, and cross-section area representing density at all points along the length. Obviously, if we stretch this wire, the cross-sectional area would reduce. And on the other hand, if we shrink it, the cross-sectional area will increase to conserve mass. So same principle applies in case of our PDFs to ensure that total probability continues to sum to 1. Going back to this uniform distribution example, if A is now 1/4 of its previous value, we are shrinking the length, and hence density at all points would have to increase to ensure that probability sums to be 1. By the way, notice that the density at all points here is greater than 1, which is completely valid because we are talking about densities and not probabilities. With our y equals 2x example, here we have stretched. So the density at all points will reduce, which means density at y equals 2, which we earlier said should be density at x equals 1, is incorrect. Now let's derive the correct relationship between these two probability densities. I'll be using a more geometric approach as I feel that leads to having more understanding. We'll have the distribution of x along x-axis and keep distribution of y along y-axis. And this is our y equals 2x line. Here I am assuming that for both x and y, the possible range of values are greater than 0. Let's say we take a point x and increase it by a very small amount dx. And we'll extend both x and x plus dx till our y equals 2x line. The area of this region is the probability that x belongs within this region. Assuming dx to be small, this area would approximately be base, which is dx, times height, which is probability density at x. And obviously the sum of such small areas over all possible x values would be 1. Because of this change dx in x, when we use the mapping from x to y, this will lead to a corresponding change in y as well. Let's call that dy. So since y equals 2x, dy will be 2 dx. Also, the probability that x belongs in region between x and x plus dx will be equal to y being between y and y plus dy. Keep in mind that I have said probability. Probability would be equal, but density, as we have seen from before, will obviously be not equal. In the wire example, take 2 points before stretching and also new positions of those points after stretching. Total mass between those points will be same. Going back to our px times dx area, we can rewrite this in terms of y. So it becomes px of y by 2 times dy by 2 as x equals y by 2. And now if you look at the right hand side, it's dy, which is our base length for this yellow region. So whatever we have multiplied this base dy with must be the probability density at y, because area of this yellow region is density at y times dy. This then brings us to our relationship between px and py. So py at y equals 2 will be px at x equals 1 divided by 2. For a more general version of this equation, which applies to any transformation from x to y, let's go back to our previous equation and replace y by 2 with x, and this 1 by 2 came from dx by dy, so replace that as well. Now these x and y are according to some transformation f, which was earlier 2x. So dx by dy is actually nothing but df inverse y by dy. So assuming our transformation function f is invertible, this is the relationship between px and py with y equals fx. As a side note, here we can replace dx by dy with 1 over dy by dx, which allows us to write this expression involving the function f rather than its inverse. This is almost the correct expression. This dx by dy term could be negative, but our probability density values can never be negative. So rather than dx by dy, we use absolute value of dx by dy to handle both monotonically increasing and decreasing functions. Looking at this expression, one can see that the density for a particular y takes into account two things: what the density of x was, and this x would be f inverse y, but it also scales this density of x with another term. If the transformation f shrinks the base dx, then the scaling factor dx by dy would have a value greater than 1, and the density of y would be larger than density at corresponding x, to make sure that the area or probability measure remains the same, like we saw for our uniform distribution example. Similarly, if the transformation stretches the base dx, like we had for y equals 2x example, then the scaling factor would be less than 1, and density of y would be less than the density of corresponding x. So how a small segment dx is transformed decides how the density gets transformed. This expression, as of now, works only for 1D case. But what about multi-dimension cases? Let's go over 2D example, and that should allow us to generalize to higher dimensions. For 2D, rather than thinking of base segment dx and area as the probability measure, we'll need to think of a base patch spanned by vectors dx1 and dx2 and height as probability density. The probability that x belongs in this base patch region would be area of this base patch times height or probability density. Similar to 1D example, any invertible transformation y equals fx would either stretch this patch or it would shrink this patch. Now if we try to compute how this small patch spanned by dx1 and dx2 gets transformed into another parallelogram spanned by vectors dy1 and dy2, then dy1 would have a term involving partial derivative of f1, where f1 is the function taking in both dimensions of x, x1 and x2 as input, and emitting the first dimension of y, y1 as output. So we will have partial derivative of f1 with respect to x1 times dx1. And another term will be partial derivative of f1 with respect to x2 times dx2. Similarly for dy2, we'll have these terms. Once you compare the areas of both the patches, which will be cross product between the two vectors before and after transformation, we'll get that the area gets scaled by determinant of this matrix. This matrix is called Jacobian, and this scaling factor is how much the base area spanned by dx1 and dx2 gets scaled by when transformed using f. To arrive at our final expression, we can again use conservation of probability, which will give us px times dax, which is nothing but area spanned by dx1 and dx2. This will be equal to py times day. We know that day equals determinant of Jacobian times dax. So for 2D case, and similarly for multidimensional cases, our expression ends up to be this, which can also be written as this. Rather than having determinant of Jacobian of f, we can also replace it with determinant of Jacobian of the inverse function. And we can do that because Jacobian of the inverse function at a point equals the matrix inverse of the Jacobian of f. And then we use the fact that determinant of A inverse is just 1 over determinant of A, as multiplying determinant of A inverse and determinant of A is just 1. Okay, so let's summarize everything that we have up till now, but this time looking at it from the perspective of transformation of latent variable z, which is coming from pz, that is a simple distribution like standard normal distribution, to our data distribution px, which would be a complex one. We define a transformation f which needs to be invertible and differentiable, because both aspects are needed for our density computation, which in turn would be needed if our goal is to train this using log likelihood. Based on our change of variables formula, we have px as pz times 1 over determinant of Jacobian of the forward mapping f. And we can express the same using determinant of Jacobian of the inverse mapping. As of now, all we have is one invertible transformation, and by taking log on both sides of the expression, we will get the log likelihood of the data point x. This is going to be just the log likelihood of the inverse latent point plus the log of determinant of Jacobian of the inverse function. If our simple distribution is standard normal, then the log likelihood of z can easily be calculated given the z returned by the inverse function with x as the input. But our transformations are constrained. We need f to be invertible, so it cannot be arbitrarily complex. And expecting some relatively simple transformation to allow us to directly go from standard normal distribution to complex data distribution might be too much. However, stacking simple transformations together can give us a complex transformation. So let's say z is nothing but z0 and the samples from data distribution is z capital N. Instead of 1, we have n invertible functions. f1 taking z0 and giving us z1, fn taking zn minus 1 and giving us zn, all the way till f capital N, giving us samples from data distribution. Now the whole chain, which is nothing but composition of n invertible function, gives us the transformation from initial latent point to data point. And since we are composing all invertible functions, the entire transformation f is also invertible. The log likelihood can still be exactly computed using the same expression for single invertible transformation f. We can use this for the last transformation f capital N, which takes z capital N minus 1 as input and gives us z capital N, which is just the data x. Now the log likelihood of z capital N minus 1 can again be expressed using change of variable theorem in terms of zn minus 2 and the log determinant of Jacobian of f inverse n minus 1. And we'll also have the log determinant term from previous step. Using the same approach, we can express log z capital N minus 2 again, and repeating this step for all z's till z0, we get to this final expression. So log px is nothing but log p z0, which is easy to compute, plus the summation of log determinant of Jacobian of the inverse of all n transformations involved in the chain. Given such chain of functions, where each function is computed by a neural network layer, we could train it using maximum likelihood. Each function fn, represented by some neural network, takes in zn-1 and learns to transform it to zn, such that after the final transformation, we end up with the data distribution. During training, these layers will go through the inverse direction, feeding the chain of inverse function our data, going through the inverse transformations, and ensuring that the sum of log likelihood of latent z0 plus the log determinant of Jacobians is as high as possible, which essentially is just minimizing negative of log likelihood of data. For sampling or generating images, we will go through the forward path. Feed our chain of transformations the sample z0 from our simple latent distribution, and hopefully if trained well, after going through the forward path, each transformation will bring us closer to our data distribution. So we start with our simple distribution and flow through this chain of invertible functions, where each function transforms the input distribution until it matches our target distribution. Using the change of variable theorem, we ensured that each step, the transformed distribution, is always normalized, hence the name normalizing flow. Hopefully by now you have clarity on training and sampling, but we still haven't talked about the design of our normalizing flow model. What I mean by that is it's easy to say that these transformations can be modeled by some neural network. But as we talked before, we can't have some arbitrary network predicting Zn given Zn minus 1 because we have two constraints for these transformations, both coming from this expression that we have in front of us. First is that all of the n transformations must be invertible and differentiable. And second is that the determinant of Jacobian can be easily computed for all these transformations in the chain, which means our neural network model, which under the hood is going to learn these transformations, must be designed in a manner that ensures that these constraints are met. There is actually an additional constraint. Our latent space and all the other variables involved in the chain must be of the same dimensionality as our data. For all the transformations, we want every input to map to a unique output, and every output value to also have an input mapping. If we are dealing with images of say shape 3 cross 256 cross 256, then all z's will have to be in this high dimensional space. This is different from VAE or GANs, where our latent space generally has lower dimensionality than data. So we have understood everything about normalizing flows. But in order to be able to train a model, we need to work with a neural network that meets these constraints. As an example, we'll next look at RealNVP, which is a normalizing flow model, and see how these constraints are met in there. The base component of RealNVP model is an affine coupling layer, and we are actually just going to look into that rather than understand each and every aspect of RealNVP. To understand affine coupling layer, we'll first assume our data is a 1D tensor, and later see how these layers can be applied to images as well. In the forward path, an affine coupling layer divides the input in two parts. One part of the input is not modified at all. Let's assume that is the first part. So the first D elements here will not be modified and directly be the first D elements of output of this layer. The remaining elements undergo a scale and shift affine transformation. But these scale and shift parameters are actually functions of the first part and are predicted by a neural network. The authors have the network predict log scale, which is why you see exponential function applied to the scale prediction. So let's see whether our constraints are met or not. First, looking at invertibility. Is it possible to get x back from the output y? Well, the first part of the output can straightaway be mapped to the first part of input, as that remains untouched. Also, since first part remains the same, feeding that to the network, which predicts scale and shift, will generate the same predictions for those parameters. Finally, the second part of the input can be retrieved by using the scale and shift computed parameters. We'll take the second part of the output, subtract shift from it, and then divide it by scale. Great. So we can easily compute the inverse of transformation applied by an affine coupling layer without actually computing the inverse of function that computes scale and shift, which means our neural network that predicts those scale and shift parameters can be really complex. On to the next constraint. Computing determinant of Jacobian should be easy. Now that does not seem plausible because if we are working with data that has dimensionality n, then Jacobian is n cross n matrix. So computing this determinant during training will end up being very costly. But let's still see what comes out to be the Jacobian. The first part of output is same as the first part of input. So in our Jacobian, this would just be identity. The partial derivative of second part of the output with respect to the first part of input would involve our neural network. So let's leave that as it is. The partial derivative of first part of output with respect to second part of input is just going to be 0 because second part of input does not impact the first part of output. Lastly, the partial derivative of second part of output with respect to the second part of input is this exponential of log scale predicted by our network for each element present in the second part. Now what we have is a lower triangular matrix, and determinant of such a matrix is just the product of diagonals. So our determinant simply becomes e raised to the power of summation of all log scale predictions made by our network. This is really great because we don't need to compute Jacobian of functions that compute scale or shift, which means a deep neural network can easily be used for those parameter predictions. In our log likelihood computation, we have log of determinant. So with this Jacobian matrix, that ends up simply being summation of all log scale predictions made by the network. This affine coupling layer then performs our transformation from Zn-1 to Zn, and RealNVP model is just a sequence of these affine coupling layers. Now you might see that since the forward transformation leaves some components unchanged, the first part of the network will just continue to be unchanged throughout the chain. This obviously is not desirable. So what the authors do is they compose coupling layers in an alternating pattern. If layer I changes the first part, layer I plus 1 would change the second part. While we discuss these coupling layers, keeping the input as 1D tensor, the same scale and shift can be done with images as input as well. Just like here we divided the input in two parts, we can partition feature maps or images, either spatially by using a checkerboard mask, which has value 1, where the sum of spatial coordinates is odd, and 0 otherwise. For one type of mask value, we'll keep the input activations unchanged, and for the other, we'll compute scale and shift and modify them accordingly. We could also partition according to channels. So first half of channels remains unchanged, and second half is modified according to scale and shift values that are going to be computed using first half channels. When we are working with feature maps, given an input x and mask b, the output y can be computed using the following expression. So if the value of b is 1, then activation at that location is going to be unchanged and be the same value that was there in the input x. Whereas if b is 0, then the activation at that location is going to be modified. Similar to how for 1D case, if layer I modified the first part, then layer I plus 1 modified the second part, for convolution layers as well, the mask is going to be flipped between alternate layers. The paper actually has a lot of other details, but for the purpose of building a simple RealNVP model, this is all we need. In paper, the authors also use a modified version of batch norm as well as a multi-scale architecture, but we are not going to go over those in the interest of time. In the next section, we'll implement a simple RealNVP model, which will just be a stack of affine coupling layers. But before moving to that, I wanted to mention few implementation details. First is that in our model, the forward path during training, which will be our model's forward method, will be progressing from input data x to z0. So our forward method would take zn as input and compute zn minus 1, one part of which would be unchanged, whereas the other part would be modified by computing scale and shift parameters. For predicting these scale and shift values, we'll try with both linear layers as well as convolution layers. Secondly, we would be training on MNIST dataset, but rather than working with images, which are of shape 1 cross 28 cross 28, we will be training our normalizing flow model on latent encodings of MNIST images obtained using a pre-trained VAE. So our data distribution would be the distribution of latent encodings of MNIST images. This is just because I was able to get significantly better results using this approach. But obviously one can train the same model on images in pixel space as well. For sampling, just like stable diffusion, we would first have our normalizing flow model generate a latent encoding and then feed that generated sample to our pre-trained VAE to get a sample in image space. Third is regarding our log likelihood computation for training. We have this expression for log likelihood of sequence of transformations. And we have seen that for affine coupling layers, the log of determinant is just summation of scale parameter prediction for all components. So the second term for log likelihood is just going to be the sum of all log scale parameter predictions over all affine coupling layers. Those were all the details that I wanted to specifically point out. And now let's move to implementation. For the implementation, since we are working with latent encodings, we'll be first training the VAE and save the latent encodings of all MNIST training images. The VAE architecture and training and even dataset class is exactly same as my stable diffusion videos. For normalizing flows model training, our MNIST data class will first load all the saved latents and then in getItem method return that. So our dataset, rather than returning the image, returns the 4 cross 7 cross 7 saved latent. The shape is such because our variational autoencoder has a downsampling factor of 4 and also has 4 latent channels. All the necessary parameters for training our model are going to be coming from this config. This section you don't have to be concerned about. This is just VAE parameters. If you're interested in going over the VAE training code, then please go through my latent diffusion videos. For this video, we are only concerned with these parameters. Conv just indicates if we are using a convolution normalizing flow model or not. In the repo, there is another config called mnestconv, which has conv as true, and that can be used for training a convolution flow model. This config that we are looking at is going to be having affine coupling layers as linear layers with RealU activation. This parameter represents the number of affine coupling layers, so the number of transformations f that we are modeling. This is the hidden dimension for the linear layers. In convolution model config, this would refer to the channels in the intermediate feature maps. Post that, we just have some training parameters like number of epochs, learning rate, and so on. This file has our entire model. Affine coupling layer module is going to represent one single transformation f. And remember, we are going from x to z in the forward method. We first check whether we are going to be building a convolutional model or linear model. Then using the autoencoder parameters in config, compute the size of latents, which would be 7 x 7, and channels in latent images, which would be 4 by default. For the linear case, we are going to have two networks, one for predicting scale, another for predicting shift. We get the total number of features that we are going to be working with, and then we'll divide the features into two equal parts. This is our sequence of linear layers that will take the first part as input and predict as many scale parameters as there are features in the second part. Then here we have our shift prediction network, which will predict as many shift parameters as there are features in the second part. In paper, the authors mention that to predict the log scale parameter s, they use hyperbolic tangent function multiplied by another learned scale factor. This is primarily for training stability, so we'll also apply the same activation to limit the scaling output from -1 to 1. But then to still allow log scale values larger than 1, we'll multiply with this learnable scale factor per dimension. We'll also apply the exponential function on this learned scale factor, and since we have initialized this as 0, this means at initialization, the log scale predicted by the network will be in the range from -1 to 1. This else part is for the case that we are building a convolutional model. In order to simplify and use the same code for both linear as well as convolutional case, I will be splitting the Z channels into two. The first set of channels will not be modified, and second set of channel activations will be modified using activations in the first set. This will make our convolutional implementation kind of similar to what we saw in channel masking. Our scale and shift networks are then going to be simply sequence of conv and ReLU activations. In paper, the authors use residual networks as well as batch norm, but I have kept things very simple here, and you are more than welcome to try with complicated networks. This is the same log scale factor in case we are building a convolutional model. Now let's move to our forward method, and this is going to be a very small one. We divide the input in two parts. If it's a linear model, then we divide along features, whereas for convolutional case, we divide along channels. Then we flip, and this flip argument will be true for every alternate affine coupling layer. Now the first part is used to compute log scale, followed by activation. Then we are going to multiply with the scale factor, but only after applying exponential function to that as well. Then finally we'll apply another exponential function to convert log scale prediction to scale prediction. We use this prediction as well as shift to modify the second part's value, and then flip it back and concatenate the first and second parts. For training, we need each coupling layer's log determinant of Jacobian. So the forward method not only returns the transformed output, but also these log determinant terms. We know log determinant is going to be the sum of log scale parameter prediction by the model. And since earlier we applied exponential function on the log scale prediction sig, so log determinant simply becomes summation of sig.log. At last, the forward method returns the transformed x and log determinant of the Jacobian of this layer. The inverse of this layer, which we are going to use to get from z to generated data point, is going to be very similar. The only difference is now after computing scale and shift, we subtract by shift values and divide by scale values. And also, just like the forward method, we do the flipping here as well. With our single affine coupling layer done, let's move to this module, which is our stack of coupling layers and will be our normalizing flows model. During initialization of this module, we first get the number of coupling layers to use. By default, for linear model, I use 12 layers. Then we define the flips for all layers in an alternate mechanism to ensure that if layer I works on modifying the first part, then layer I plus 1 works on modifying second one. These are our n affine coupling layers, and our prior PZ is just going to be standard normal distribution. In the forward method for our flow model, we need to sum the log of determinant of Jacobians of all coupling layers to compute the log likelihood. So we keep saving that for each layer in this list. Then call each of those layers with the previous layer's output as well as flip values. The first layer during the forward call will just be receiving a sample from our dataset. From the final x, which is nothing but z0 prediction, we compute its log likelihood according to our prior, and then the forward method returns the z0 prediction as well as two terms required to compute log likelihood px, log of p z0 and sum of log of determinants of Jacobians of all coupling layers. The inverse of our normalizing flows model just applies these coupling layers in reverse direction, going from a sample z0 from our prior to a prediction zn, which hopefully will end up being close to a sample from our data distribution. This is all that's needed for our normalizing flows model. Moving to our training script, where we first fetch all the necessary config parameters, create our MNIST dataset class, instantiate the model, and load our pre-trained VAE as well. This pre-trained VAE is actually not needed for training. I just visualize the generated samples every few steps, so that's the only reason of having VAE in the training code. The authors of RealNVP use weight decay for the log scale factor predictions, so we also use that. Now getting to our training loop, where we are going to fetch our latent. For every image during VAE inference, we would have saved mean and log variance predictions for the latent encodings. So once we get these from our dataset class, we use reparameterization trick to generate our latent image for training. A side note here, if we are going to be training on images, like say images from MNIST dataset, then those have discrete pixel values rather than continuous. So if we train our flow model on these, it would learn a degenerate continuous distribution with really high density spikes at different discrete values that it has seen during training. A common technique to avoid this is by dequantizing. And a simple way to do that is to add small amount of noise to each pixel value. And then the pixel values are scaled from 0 to 1. This ensures that flows can model images with discrete pixel values as continuous distributions. During sampling, we would again quantize the generated sample to get our image with discrete values. Okay, back to training code. Our latent images would be 4 x 7 x 7. So if we are working with a linear model, we need to flatten this latent image. And after that, we'll call our model's forward method and train using negative of log likelihood. Before finishing with implementation, let's also quickly take a peek at the sampling script. And in here, after we have loaded the model, we call this sample function, which first computes what should be the shape of z0. For our case of convolution model, it would be 4 x 7 x 7, and for linear model, it would be 4 times 7 times 7. We call the model's inverse method with this z0, and it will return zn, our generated latent sample. Then after reshaping it to 4 x 7 x 7, We feed it to our VAE decoder to get our generated image sample and save that image. After training our normalizing flow model on MNIST dataset, this is the kind of images that we end up generating. And these are from our linear model, which has 12 coupling layers. This is the sample output from our convolution model, and that has 6 coupling layers. We can also look at all predictions from Z0 to Zn to see how progressively each successive transformation generates a more digit-like image, with the final sample looking very similar to images present in our MNIST dataset. That brings us to the end of this video. There are a lot of aspects which I could not cover in this video because of time constraints, specifically the different papers on normalizing flows like NICE, which was prior to RealNVP and used additive coupling layers. I also did not cover some aspects of RealNVP as well as GLOW, which is another normalizing flows model that uses invertible 1x1 convolutions in addition to affine coupling layers and gets really good generation results. So in case you are interested in normalizing flows, then please take a look at them as well.